Okay, so let's go, that brief interlude, we'll go down to the model of our system. And so modeling flux-pinning, there's really one major model that's been out there that doesn't involve trying to integrate over all of the little things happening in the superconductor. And this is Korjuk's image dipole model. Now the image dipole model has two assumptions built into it. That is basically the assumption that you're using dipoles. So this is pretty accurate for what we're doing in our lab actually, because we're using cylindrical magnets and they're fairly small. So we're okay with this assumption. The second assumption is that your superconductor is an infinite plane. And clearly, as you saw, that the YBCO effect is not an infinite plane, and so we're neglecting edge effects in this particular model. However, at distances very close to the superconductor, this can be a pretty decent approximation, and the actual effect you see of flux pinning decreases rapidly in this nonlinear way that I described earlier. So as the edge effects will become more prominent, the flux pinning effect is kind of dying off anyway. So these are fairly good assumptions for what we need here. Okay, so the idea is that at a temperature above 88 Kelvin, I picked that because that's our YBCO, but it would be the critical temperature for whatever superconductor you're using. The image dipole model basically says that the magnet and superconductor just don't interact. It's just a ceramic and a magnet. However, when you cross it below this critical temperature, you've established an equilibrium point. So the equilibrium point in this model will actually have something called an image reflected in the superconductor that it then responds to. So the first image is a frozen image, and this is basically a mirror over the surface of the superconductor of your magnet in the same dipole direction that's stuck in that place that you picked. So these two are attracting right here in that sense. There's another image that gets put into this model, which is called the mobile image. Now the mobile image is in the opposite dipole direction of your magnet. So as you move the magnet around, you can actually see that it will reflect over the surface of the superconductor wherever your magnet goes. Now the end result of this is that, again, your frozen image stays here, and this is an attractive potential well. So at your equilibrium position, this is providing an attractive basin back to your equilibrium. The mobile image, on the other hand, is providing a repulsion force because the dipoles are in opposite directions, so they're trying to repel each other. So what you get is a repulsion here that tries to flip it back into its potential well. And so this is a way to kind of characterize how the flux pinning system actually works. Now, one of the interesting things about this, and this is kind of the thermal reaction I talked about, actuation I talked about before, is that once you've raised that above 88 Kelvin, all of your images disappear. And again, you've got a blank slate. But as soon as you cool it into that position again, you've now fixed your frozen image and your mobile image in that new configuration. So you can do this as many times as you choose, and it's a very flexible system in that sense. You can also point out that at each equilibrium position, the mobile image and your frozen image dipoles actually cancel out. So in its equilibrium, the magnet experiences no net force. Okay, so to kind of do a simple Lyapunov analysis on this, we know it's stable from empirical evidence, but just to show it in theory, we're going to use a common method of finding a Lyapunov function is using a total energy of the system. It's very convenient, it has very physical meaning, and it tends to follow the three characteristics of Lyapunov functions that I described before. So here we're going to have our Lyapunov function, which is V, and we're going to have our total and potential energy added up. So the total kinetic energy that we've got here is actually only related to the magnet. So the magnet's the only thing that has mass. These are just kind of virtual images that don't actually add any kind of kinetic or potential energy to the system. So we have our just standard rotational and translational kinetic energy. And then finally, the potential energy that comes from here is actually as a result of the total magnetic field that these images produce. So each of these has a dipole magnetic field that gets summed up to produce a force and torque on this particular magnet. So the sum of that magnetic field, when you project this dipole onto that magnetic field, you get the resultant potential. If you took the gradient of that, you'd actually get the forces. Okay, so that summation is our Lyapunov function just for a simple flux-pinned system. Now let's move into what an actual docking interface would involve. So you again see our familiar model here. We've got our field cool position, or our equilibrium that we've set it at. We have our frozen image in blue, we've got our mobile image in green, and we've got our standard magnet in red. Now we can actually start adding variables to this. So we've got our dipole vectors, which are just going to be denoted by n's. We've got our bunch of position vectors, which are denoted by r's. And we can actually add our system values to this. So we are actually adding a cube, in this case you'll see a couple images here. We're adding a cube spacecraft to our model here, and this is going to be fixed in that position on the cube itself. So once you have this, and you also have the normal of your superconductor, excuse me, you can get the relative vectors. And again, I was talking about close proximity rendezvous, so we really need to worry about the relative vectors of everything. So we've got all of our relative vectors. And this constitutes the basic work of a simple model with just one magnet in it. Now if you were to add additional magnets to this, so for example you field pooled a different magnet right next to it, you would basically get another field image and another mobile image that followed it around. And now you have to take into account the cross terms for each one of these. So this frozen image will affect both magnets. It'll try to attract it to that basin. Now, if you did not field pool something, so for example, if you had an electromagnet on board, so if this second magnet was an electromagnet and you started it without any kind of energy, you would end up not having a field cooled position. There would be no image. It's essentially, the field cooled image is at infinity, if you want to think of it that way. So it's still the same model, but it's just negligible since it's at infinity. So you wouldn't get a field cooled position, but you'd still get this mobile image. So you'd basically get an additional repulsion force, and you'd still be attracted to this potential well by that magnet. Okay, so going back to the system that we have here, considering only one magnet for now, the updated model that we basically have will change two terms really in our equation of motion. We've got our control, and this system will include some damping. As you saw in the video that we had, it's a fairly well damped system. And so that we have some damping in our equations of motion to model that. So when we take the derivative of our Lyapunov function, you can actually see that these terms here are basically the equations of motion. You've got your acceleration times your mass, etc. So if you plug in those equations of motion from the left side into this, you can actually see that our control term and our damping enters into our Lyapunov function now. So the condition for the guaranteed Lyapunov stability again is that your derivative of your Lyapunov function must be negative semi-definite. So since this energy in this case, or version of energy here, is a scalar, and so basically it's less than or equal to 0 is the condition you need. So if you actually plug that in there and do out the math, you get a condition on a Lyapunov guaranteed stability. So here you've got basically that your control input when projected over your velocities has to be less than the sum of the damping that you see in your system. So again, the violation of this condition, because this is a Lyapunov proof, does not imply instability. It just knows that if this is true, you definitely have a stable system for that particular case. So meeting the condition doesn't guarantee stability, but if it does not work, you might have to go back and find a different Lyapunov function, or you might have to find stability in a different way. It doesn't necessarily imply that it's unstable. Okay, so what we're going to be doing with this, and what's in progress right now, is we've actually got a simulate model of the full nonlinear dynamics, and that's currently being implemented to be able to simulate this a little bit more and actually see how this kind of interaction might respond under various circumstances. We also are working on a test bed for the experimental side of things. So we're working with something called a Flux-Pinned, which is a 3-degree freedom test bed for validation of these basic control concepts and being able to actually work with this condition that we have. So the Flux-Pinned test bed is basically, this is a module of it. There was a talk by William Wilson earlier today that got into more detail, and you can actually look up that paper if you're interested in the details. But essentially, it's got a payload on the top, and it's got several air bearings and a little pressurized air system down here to allow it to float on glass. And so what we've done is we've actually taken 2 of these, and we put some magnets on one side and some superconductors on the other that right now we're cooling with liquid nitrogen. And we've got a little bit of some video. These are all very preliminary, but this was up and running just last week, and I wanted to show you guys some exciting things. So the magnets are on this side. I apologize for the choppiness of the video. It's not like that normally. So what we actually are seeing here is that this is a Flux-Pinned docking interface. You've got a Flux-Pinned system where you've got YBCO on one side, you've got your magnets on another, and they're staying at the position that we cooled it at, which is about 1 centimeter. And so right here, you can see that you can drag the system, and the attraction well is actually strong enough to bring all of them together. You can repel it by pushing one module, and they both try to seek that same equilibrium, and they stay together. So it's a very exciting, in fact, you can see it right there, as it drags around. So this is a very interesting implementation. You can see here how a docking interface might occur at a obviously very close range here for this particular size of superconductors and magnets. But again, that's what we're kind of going for. Ultimately, we'll be putting an electromagnetic series on there. We've already got that designed, because we're finally going to be doing a microgravity flight experiment with this. And so we're building off work that we did last year. We actually flew a Flux-Pinned interface on a microgravity flight in the previous year. And so this year we're actually, that was a pure passive system. We just stuck the superconductors on there and the magnets on there and saw what happens. Whereas here we're actually, for this year's microgravity flight, which is going to be on the 27th of September through the October 1st of this year, we're actually putting a series of electromagnets on there, and we're going to be actively, autonomously controlling it on board. So it's actually got some Bluetooth and some IMUs on here, and they actually communicate with each other to give relative position data between the two, and we'll be able to get it to autonomously come together, flux pin and its interface, and then be able to change its equilibrium as we choose. Okay, so to kind of summarize here, the paper that we're talking about is proposing a new augmentation to current close proximity docking, known as Flux-Pinned docking interfaces. And from this, we have 4 characteristics that we're really going for. This particular paper focused a lot on condition for stability guarantees. So we developed a model that is a full nonlinear model that should be up and running very soon in Simulate. We've got our Lyapunov analysis that gives us conditioned for a first cut at what kind of force we might be able to, what kind of control force we might be able to use. And then finally, we're going to be, we're in the middle right now of actually implementing this and simulating it on these flow cubes. The other things, however, have not been forgotten. So as future work, we're going to be working on the flow cube and the Ragnar, the microgravity flight test beds. And these will hopefully be able to show safe failure modes and this kind of dynamic response. So I described the Ragnar system being able to dynamically alter its equilibrium in microgravity. We're also hoping to be able to simulate a control failure. So we have the 2 docking spacecraft come together, and one of the control systems cuts down. We will see the dynamics of that and hopefully show that it has safe failure modes. And finally, for this optimized performance, this is something that's kind of a more distant future work, but we're really interested in looking at how to optimize this kind of system for time of interaction, or perhaps minimum fuel or electricity or something like that. So I'd like to acknowledge Joe Shore, William Wilson, and Mike Norman for all of their help and everything. Mason, that was a great help, and all the people in the Ragnar team and the Space Systems Design Studio at Cornell. If you're interested in learning more about some of our flight projects and some of our research, we have a website, spacecraftresearch.com. It has a lot of really interesting videos and some of our papers on it. And with that, I'll take any questions.